So we have a handful of random one-off topics that we occasionally need to cover, and one of them is degrees of unsaturation. And the key thing I'm going to point out here is that there actually is a formula in your book. And if you're the sort of person who just likes to memorize things, you absolutely can memorize this, and then you're fine. Having said that, I can never remember exactly what the details of the formula are, so I always have the ability to regenerate things. There are times in this course where, like nomenclature, you simply need to memorize things because there is no alternative. You have to memorize it. And then there are definitely places where you can kind of work it out as long as you know kind of what you're going for. So the whole point of degrees of unsaturation, the reason why we care and the reason why we store this away, is if you are given a NMR problem, which is something that we're going to do later in the course, you're going to have a much better chance of figuring out what the identity of the molecule is if you have a molecular formula in mind. And so the question is, what are the expected numbers of hydrogens associated with a single carbon or two carbons or so on and so forth? And how does that get affected by the different functional groups that are attached? And if you're short a couple of hydrogens, what does that mean? So, okay, let's just first establish how many hydrogens are associated with a given carbon. So, if I have methane, that's CH4, and it's drawn that way, but what I'm going to do here is just simply write the number of hydrogens associated with the number of carbons. Ethane, this is a CH3. This also is a CH3. Therefore, this is C2H6. Okay, how many carbons do we have? Well, we have 3, and this is a CH3, and this is a CH3, and this is a CH2. So in other words, this is C3H8. And you can keep going, and I'm sure you're going to notice a pattern developing over time, but the total number of hydrogens is always 2 more hydrogens than twice the number of carbons. So in other words, you could be 2 times the number of carbons plus 2 is the number of hydrogens bound. And that's what I'm saying. There's a formula. You can figure this out. But the other thing I would say is this makes sense because a methyl is always a CH3, and then here you always have 2 hydrogens on methylene. So in other words, normally what you have is 2 hydrogens per carbon, but the ends of the molecule will have 2 extra hydrogens, 1 on each end for the methyl. So this would be C5H12. Okay, so how does the presence of an oxygen affect things? How does it change the number of expected hydrogens? Well, an oxygen really doesn't. So a propyl has C3H8, and propyl alcohol is also going to have CH3, CH2, CH2, H. So this is going to be a total of 8 hydrogens plus 1 oxygen. So this is going to be C3H8 O as the actual molecular formula. Likewise, it doesn't matter whether you have the oxygen at the end of the chain with hydrogen bound or the oxygen in the middle, this ethyl methyl ether is also going to have CH3, CH2, CH3. So this is going to be 3 carbons, 8 hydrogens, 1 oxygen. How does the presence of a halogen, like a chlorine, affect things? Well, to a first approximation, what happens is that the chlorine slots in instead of one of the hydrogens. So one of the hydrogens is missing because the chlorine took its place. And that's different from the oxygen. When you put the oxygen there, the hydrogen just ends up on the outside. You put the chlorine there, you replace the hydrogen. So this should end up with 3 hydrogens, 2, 2, 2. So that's 6, so 9. So this is going to be C4H9 Cl. And it doesn't matter where that chlorine goes, you're going to end up with the same exact scenario. So what a chlorine, a bromine, an iodine, what they do is replace one of the hydrogens. Fluorine as well, for that matter. Okay, what does a nitrogen do? Well, something odd. What it does is add an extra hydrogen. This molecule right here has a methyl, so that's 3, 2 hydrogens, 2 more hydrogens, 2 more hydrogens. So 6 hydrogens total there, plus 3 there. So this is going to be C3H9N. The nitrogen adds a hydrogen to the system. Again, this has 3 methyl groups, so you're going to see that it's C3H9N, and likewise here, methyl, 2 hydrogens there, methyl, 1 hydrogen there. So this is all going to be, again, C3H9N. So the moral of the story is that the key thing to keep in mind is the total number of hydrogens you expect to have is given by 2 times the number of carbons plus 2. In other words, the number of CH2s plus 2 hydrogens for each methyl. Oxygens don't change the hydrogen count. Nitrogens increase the hydrogen count by 1. Halogens decrease the hydrogen count by 1. So this is the expected number of hydrogens present. Okay, so all I've done so far is establish the expected number of hydrogens for a given number of carbons. So a single carbon should have 4 hydrogens, but 2 carbons should have 6 hydrogens, and so on. All of these molecules, though, have a degree of unsaturation of 0. They have all the hydrogens that they should. Meanwhile, all of these molecules here have double bonds or rings. They will end up with degrees of unsaturation that are higher than 0. They're going to be at least 1. They're going to be unsaturated in some form. So this molecule right here, how many hydrogens does he have? Well, he has 2 right there, 3, 4, 5, 6. So this is C3H6. This, of course, should be compared to the propyl chain that it came from. This has 1 double bond. This is a degree of unsaturation of 1. Likewise, this molecule right here has CH2, CH2, CH2. This also would be C3H6, and once again should be compared to C3H8, and so it also has a degree of unsaturation of 1, and in this case it's because a double bond and a ring are fundamentally the same idea. This is a relatively small ring, but a double bond is the smallest ring you can have. It's a ring of 2, essentially. So the presence of a double bond or a ring means that you have a degree of unsaturation of 1. This molecule here, with 2 double bonds, would have a degree of unsaturation of 2. But if you're thinking in terms of the number of hydrogens associated, well, it should be C4H10, but in fact has 2 hydrogens there, 2 hydrogens there, 4, 5, 6. So this is going to be C4H6. Now again, the key thing is that you have 2 double bonds, you can see that, so the degree of unsaturation is 2. But the key thing to keep in mind in terms of figuring it out from the other direction is that if you have 2 hydrogens less than you should, that's a DU of 1, and that's true for each additional one. So here we have 6 hydrogens instead of 10, so that means we're missing 4 hydrogens, which means that it has either 2 double bonds or 2 rings. It has a degree of unsaturation of 2. A triple bond is, of course, just simply 2 double bonds, so this also has a degree of unsaturation of 2. And again, if you were to work through the number of hydrogens associated, there'd be a methyl there and a single hydrogen there, so this is going to be C3H4, and so this is missing 4 hydrogens relative to this C3 molecule, which is why it's a DU of 2. Okay, what should a C6 molecule have? So C6 type molecule should have a total number of hydrogens that's equal to 2 times the number of carbons, 12, plus 2, so that would be 14. So C6H14 is what you should have. So how many hydrogens are in benzene? Well, this is C6H6 if you work through it. So benzene has C6H6, but it should be H14 for the 6 C's. So in other words, how many hydrogens are we missing? Well, there are 8 hydrogens missing of what could be the maximum. So in other words, DU for a benzene is 4. 1 ring, 3 double bonds. The reason why I point this out is because you're going to be working with many, many, many benzene rings, especially in the lab. And so if you see a DU equals 4, you should start thinking about a benzene ring as a possibility. Right now, this seems a little bit out of context. The reason why I'm bringing it up now is because you're starting to think about line angle structures and nomenclature and trying to figure this stuff out. In the big scheme of things, we're largely going to start applying this when we start dealing with NMR. But it's worth thinking about now.